Hi, a very warm welcome to one and all present here. My name is Akash Arya, and I am the student of MTech here at MEMS department, IIT Bombay. So today I am going to discuss the case study presentation of MM641 numerical methods course, and let's begin with the title. The title of the paper that I am going to present is a study on numerical integration methods for rendering atmospheric scattering phenomena. So basically, the objective of this paper is to find the color of the sky using single scattering phenomenon. Okay, let's discuss the physics of the problem or concept behind it. So basically, in the atmosphere, we know the two scattering are there, and so we know for the where the radius of the particles is much less than the scattering wavelength. That is the Rayleigh scattering. So basically, it is for smaller particle, and my scattering is basically much greater than or the scattered wavelength, or basically the no, for the larger particles. So there will be larger particles, so there will be a my scattering, right? So we can directly say the my scattering is found in the lower atmosphere because of their larger radius, and the relay scattering is found on the upper atmosphere. So so we have seen the relay depends on the wavelength of scattered light, but somehow whereas my scattering does not. So we basically see in the first picture you can see like the blue sky, beautiful color. So that is because of the relay scattering, and the another one, the halos around the sun and fog and clouds. This is because of my scattering, because these are made in the lower atmosphere. So that's why we say the my scattering is found on the lower atmosphere, and the relay scattering on the upper atmosphere. Okay, let's talk about the mathematical background. So we are here using only the single scattering phenomena. So what is the single scattering phenomena? Where the only one light scattering even is taken into account. But for the multiple scattering phenomena, we have number of lights, right? This is a simple concept. And why we are taking this single scattering phenomena? Because this is easy to observe, and complex. Less complex than multiple scattering, and because it is sufficient to observe our uh, objective, right? So this is the semantic of single scattering, how it is being calculated. So this is graph where the incident intensity is coming in terms of lambda in the direction of L, and after the scattering at point P, it is going in the direction of V, where we are calculating the intensity of scattering of relay and my scattering when it reaches to observer's eye. So basically, there is a formula like where we are finding the scattering in terms of relay and my. Uh, there's a one that is coming. I1 is coming from in the direction of L from PC to P, and after scattering, the rho is a density function for the relay and my scattering, and it is changing with the altitude h, right? So when h will be larger, it will increase, right? If h will be lower, then it will decrease. And f is our phase function in between in terms of theta, angle between L and V, right? And beta is basically our scattering coefficient. So superscript of S is represent the scattering coefficient in terms of relay and my scattering of lambda, right? So beta is basically a main function for defining the color of the sky. Okay, so we'll see in the next slide. So beta is basically a scattering coefficient. So it is depends on the n square. N is the refractive index, and n is the molecular density, and also on the lambda to the inversely lambda to the power 4. So basically, when a scattered wavelength will be less, then beta will be more, and scattering wavelength will be more, then beta will be less, right? So it depends on the inversely proportional to lambda to the power 4, right? So this is the basic, because of the sky beta is the main reason. Okay, so when we see in the diagram, like at the sun zenith angle during the day, so we are getting the yellowish or white sun in atmosphere, but at the sunset or sunshine we are getting the reddish or yellowish color. So basically at the sun zenith angle during the day, the blue or violet line has a shorter wavelength, so it directly scattered away, scattered to the observer's eye. Because of the less atmosphere, less there will be less scattering, so there will be, then we see the blue sky or white sunlight. Okay, but in the sunset or sunrise, there's a the blue light has to cover long distance, right? So it is scattered away from the atmosphere. The only light, red or yellowish light, reach to the observer's eye. So that's why we see the orange red sky or sun, mm, orange sun or red sun, right? So this is the reason basically why we get, during the day we see the sun as a yellowish or white, right, or blue sky, but at the sunset or sunrise we see the orange red sky or sun, right? Now let's begin the single scattering phenomena. So this is the basically the definition. Single scattering phenomena we have already discussed. This is the formula from where we'll have to calculate via integration. And here T is the transmission coefficient that is coming from the P to PC. So we can see in the graph. So it is coming from P to PC and P to PA, right? P to PA. Okay. So that is the transmission, how light is transmitted into this. And the final intensity, if we want to, the total intensity, that is scattering of relay plus scattering of my scattering. So that will be the total scattering. Like now let's come to the how we are finding that, what is the phenomena or methods we are finding. So these are the numerical integration method, and these are the widely used numerical integration method. So one of the trapezoidal rule, we are using trapezoidal rule, where we are taking the these straight lines, making the trapezoid or trapezium, and we are calculating for every trapezium the area we are calculating, and after summing this we get the integration, right? So but in the midpoint method, we are taking like parabolic arc. So that's why we have more error relative to trapezoidal error if we compare trapezoidal and midpoint. But in Simpsons we are taking some type of arcs that makes the uh, rectangle type curve, rectangle type structure, and then we calculate the area of this block. Okay, then we find the integration via Simpson rule. So these are the basic concepts related to numerical integration methods, and these are the using via calculating the sky of the colors and sun, right? So let's how we are comparing with these three phenomenon. So each selected numerical integration method is being compared in three cases. Whether we are taking the different integration steps, how many steps it is taking, like in the low quality on when it is coming from V, and the sample on L after the scattering. So for the low quality we are taking 16 and 8, for the medium quality 128 and 64, and for the high quality 512 and 256. So so we are comparing via these for low quality, medium quality, and high quality, right? And we have all, so it has also generated the image related to some uh, criteria, like so on the different times of day or Sanjanit angle. So we have found the sky dome renders image and absolute and relative luminance image, and chromicity, and for relative error comparison. So we have also taking images of these these some of these properties, right? So we'll discuss for the sky dome standard. So basically last two of this Lebret, and this is the measurement that is from the Brunetton frameworks. We are so these three methods are compare we are comparing with these two measurements and Labrador trend. Like so for these are the cases for low quality, case 2 is for medium quality, and case 3 is high quality. So we can see in the that's we are taking cases low quality, medium quality, and high quality. For the high quality, we are taking more sample, right? And for the medium quality, there are some in between the samples of low quality and high quality, right? So that's why we have categorized in these. They have categorized these three, like, okay, for low, medium, and high quality. So if we see these three in comparison to others, so these three are basically more darker region or darker, okay. So but for the if we one can take the closer look, so trapezoidal look they have a darker sky domes at sun zenith angle at 87-degree. Color of the boundary are more, and we see the color of the boundaries, like color of the boundaries are more yellow, orange and yellow than reference lab red trend and measurement. So this is the difference, this basically. So these are more darker than the measurements or reference, like another two, right? Now let's come to the absolute luminance. If we compare with these three with these two, the measurements and laboratory, trapezoidal rule for case 1 generates washed luminance at sun zenith angle. So trapezoidal rule will have a washed luminance case at for low quality at sun zenith angle, but for all cases the Simpson's rule have a lowest luminance difference compared to the reference, right? So this is the absolute luminance. And now come to the relative luminance. We have defined the again for three qualities. So trapezoidal and Simpson's rules for low quality. So if we take talk about the low quality image, so better relative luminance than for higher quality. So for trapezoidal and Simpson's rule, low quality has a better relative luminance than the high quality image. But for if we take the high quality images, midpoint rule has a its opposite. Like so, midpoint rule has a greater relative luminance for high quality, right? Now come to the chromaticity. So for medium and high quality cases, orange color at the horizon is fading out slowly. So if we see the zoom or closer look to all the three, so the orange color is for medium and high quality case. Okay, the orange color is basically fading out, right? If we go to the right to left and compare with these others, so there is a more bluish. The liberal trend is more bluish than the other three methods. So it is fading out actually, right? Now come to the root mean square error. So for the low quality case, if we talk about the root mean square, so worst result for trapezoidal rule and relative error also biggest for trapezoidal rule. If we talk about the low quality case, and most accurate is Simpson method, and most accurate is Simpson's method. Okay, and for the medium quality, less error for trapezoidal rule, but not very different from others. It is same like, but for high quality, every method has a same root mean square error. Right, so we found here. So let's we have discussed all the images we they have taken. Now let's come to the conclusion first. So data we have seen the all the methods work very similar, and when one wants to use less sample, like for low quality, midpoint and Simpson's rules work well, and trapezoidal rule is superior when we need more sample or large sample, like when or we can say case to medium quality also. So and if we do the indefinite or arbitrary numbers of samples, so it will not affect the final image, right? So it will generate the accurate result, like so these are the some references from where I have found the mm, these papers and everything, and bibliography. uh, okay, thank you so much everyone for attending my or watching my this lecture or case study presentation. And if you have any queries and any clarification, please let me know. Otherwise, we'll end this presentation. Okay. Thank you. Thank you so much, everyone. Thank you.